What happens when an unstoppable force meets an immovable object? In the cosmos, the question is even stranger. What happens when a black hole collides with a white hole? First, let's set the stage with these cosmic titans. A black hole is a region of space-time where gravity is so intense that nothing, not even light, can escape. It's a one-way trip. Its boundary, the event horizon, isn't a physical surface, but a point of no return. Cross it, and all paths in your future lead to the singularity at the center. Time and space themselves become warped, with the flow of time pulling you inward as inexorably as the flow of space. A white hole is its perfect mathematical mirror in Einstein's equations of general relativity. It's a region that nothing can enter from the outside. Instead, matter and light can only pour out. We have never observed one. If they exist at all, they would be incredibly unstable. Any speck of matter falling toward a white hole would be catastrophically blue-shifted, gaining infinite energy and collapsing the white hole into a black hole instantly. They are ghosts in the machine of physics. So how could such a fragile object even exist long enough to meet a black hole? For this thought experiment, we need a special setup. Perhaps the white hole isn't isolated, but is the far end of a wormhole, an Einstein-Rosen bridge connecting two distant points in space-time. Or maybe it's a fleeting bounce, a momentary rebound from a collapsing object, predicted by some speculative theories of quantum gravity. Now imagine them on a collision course. The black hole is an engine of destruction, dragging space itself inward. Any nearby gas is superheated to millions of degrees in a swirling accretion disk. Powerful magnetic fields twist and snap, launching colossal jets of particles outward at nearly the speed of light. The white hole, in stark contrast, does the opposite. It's a cosmic blowtorch, relentlessly pushing matter and energy out into the universe. An unstoppable inflow meets an immovable outflow. As they draw closer, the gravitational chaos intensifies. The immense tidal forces would stretch and squeeze space-time itself, sending powerful ripples, gravitational waves, racing across the cosmos. The stage is set for a confrontation that pushes the laws of physics to their absolute limit. From this cosmic duel, theorists predict three main outcomes. Outcome 1 is the most straightforward and the most likely. The white hole simply cannot survive. Its defining feature, that no entry border, is fundamentally unstable. The overwhelming gravity of the approaching black hole destabilizes it completely. The white hole's event horizon collapses, and it effectively becomes just another meal for the black hole. The result, a single larger black hole, surrounded by a violent, final flash of radiation as the white hole's last gasp of outflowing matter is slammed back inward by gravity. Outcome 2 is more exotic. If the white hole is the exit of a wormhole, the collision is catastrophic for the wormhole itself. As the two event horizons touch, the delicate tunnel connecting them, the wormhole's throat, is twisted and pinched off. It snaps shut faster than any signal could escape. All the energy trapped within that collapsing bridge is violently released, shaking the fabric of space-time. This would create a unique gravitational wave signal, a sharp, high-frequency burst, followed by the settling ring of the newly formed, larger black hole. Outcome 3 takes us to the edge of known physics, into the realm of quantum gravity. In some of these speculative ideas, the singularity inside a black hole doesn't exist. Instead, matter collapses to an extreme density and then bounces, briefly transforming into a white hole. If our two objects meet during this phase, the collision could trigger an explosive, premature bounce. We'd see a short, blindingly powerful burst of energy, far more than a standard merger, before gravity inevitably wins. The chaotic pair would then settle into a single, quiet black hole. This all sounds like science fiction, but could we ever actually detect such an event? How would we know we weren't just seeing two black holes merge? We'd need to look for a very specific set of clues. The gravitational wave signal would be the first hint. A standard black hole merger produces a clean, predictable chirp. A white hole encounter would be messier. We'd look for a signal that starts normally, but then abruptly spikes with extra high-frequency tremors from the violent collapse or bounce. But that's not all. Unlike a pure black hole merger, this collision would be bright. We'd search the sky for a corresponding prompt flash of gamma rays, a hard X-ray afterglow, and perhaps even a faint spray of ghostly neutrinos. Finding such a signal would be revolutionary. It would be the first evidence that white holes are more than just a mathematical curiosity. It would challenge our understanding of thermodynamics and the arrow of time, and provide the first real observational window into the theory of quantum gravity. But for now, white holes remain hypothetical. This cosmic collision is a story told in equations, a thought experiment at the furthest frontier of physics. Still, it is these questions at the edge that drive us forward. For now, we listen to the waves, watch for the flashes, and let our relentless wonder pull us toward the unknown. Because even imaginary doors can point the way to real discoveries. Fade out.